out that we can certainly improve on this program because it's a little disappointing that I'm cutting this corner and saying hello, comma, and then on a new line, printing out name. Like, we can do better. And most programs you use on your phone or your laptop certainly keep text together when people want. So how can we go about doing that? Well, there's a few different ways. And in fact, the goal here is not so much to solve this one problem, but to demonstrate and emphasize that in programming, Python and other languages, there's so many ways sometimes to solve the same problem. And here's one way to solve this problem. Let me go in here, and let me go ahead now and say hello, comma, and let me just add to the end of that the user's name. So I'm using plus in kind of an interesting way. This is not addition per se. I'm not adding numbers, obviously. But I do kind of want to add the person's name to the string of text, hello, comma. Well, let me go now down to my terminal window and run Python of hello.py again. Enter. What's your name? I'm going to type in David. Enter. OK, it's better. It's better, but there's a minor bug, albeit aesthetic here. There's missing space, but let's just use some intuition here. Well, if I'm missing the space after the comma, why don't I go ahead and just add it manually here? Let me now rerun the program, Python of hello.py, enter, David, enter, and there we go. Now we have something that looks a little prettier in terms of English grammar, hello, comma, space, David. And now if we rewind, you might have noticed before or wondered why I had this seemingly extra space after my question mark, namely here. There's a space after the question mark but before the double quote, and that was just for aesthetics too. I wanted to move the user's cursor one space to the right so that when I type their name, or they type their name, it's not immediately next to that same question mark there. But there's other ways we can do this. It turns out that some functions, print among them, actually take multiple arguments. And it turns out that if you separate the inputs to a function, the so-called arguments to a function, with a comma, you can pass in not just one, but 2, 3, 4, 5, onward. So let me go ahead and pass in not just hello, comma, space, but that followed by name. And this is a little confusing potentially at first glance, because now I've got two commas, but it's important to note that the first comma is inside of my quotation marks, which is simply an English grammatical thing. The second comma here is outside of the quotes, but between what are now two separate arguments to print. The first argument is hello, comma, space. The second argument is the name variable itself. So let's see how this looks. Python of hello.py, enter. What's your name? David, enter. OK, I've kind of overcorrected. Now I've got two spaces for some reason. Well, it turns out, and this is subtle, when you pass multiple arguments to print, it automatically inserts a space for you. This was not relevant earlier because I was passing in one big argument to print all at once by using that plus operator. This time I'm passing in two because of the comma. So if I don't want that extra space, I don't need to pass in one myself. I can just do this. And now notice if I run this program again, Python of hello.py, type in my name, David, now it looks grammatically like I might want. Now, which of these approaches is better? This approach uses a function print with two arguments, hello, comma, and the name variable. The previous version, recall, technically used one argument, even though it looked a little curious. It's one argument in the sense that the computer, just like mathematicians, are going to do what's inside of parentheses first. So if inside of parentheses you have this string of text, hello, comma, and a space, which I need to add back, then you have a plus, which means not addition per se, but concatenation, to join the thing on the left and the thing on the right. This ultimately becomes the English phrase, hello, comma, space, David. And then what's being passed ultimately to the function is technically something like this. But it's doing it all dynamically. It's not me typing in David as I discretely did earlier. It's figuring out dynamically what that value is after concatenating hello with the value of name and then passing that ultimately to print as the sole argument. Let me pause here to see if there's any questions on numbers of arguments now to functions.
Can we use a function many times to solve a certain problem which we can encounter many times in our code?
You can. You can use a function many different times to solve some problem. What we'll soon see, though, is if you find yourself as the programmer solving a problem the same way again and again and again, it turns out you'll be able to make your own function so that you don't have to keep reusing the basic ones that come with the language.
I was curious about the comma and the plus sign. So after plus sign, can we give just one variable, and after comma, can we give multiple variables? Like, what is the difference?
A good question. So in the context of strings, and I keep using that term, string is a technical term in a programming language, and again, it means a sequence of text, a character, a word, a whole paragraph even. So the plus operator is not just used, as we'll see, for addition of numbers in Python like we do on paper pencil, but it also is used for concatenation of strings on the left and the right. If you did want to combine not just two strings, left and right, but a third and a fourth, you can absolutely keep using plus, 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 and chain them together, just like in math. Eventually, that's going to start to look a little ugly, I dare say, especially if your line of code gets long. So there's better ways that we'll actually soon see. And a good question as well. Well, let me come back to the code here in question and see if we can show you just a couple of other ways to solve the same problem, along the way emphasizing that what we're technically talking about here, yes, are strings, but there's even a technical term for these strings. In Python, it's just str, so to speak. STR for short for string. As you may know, if you programmed in other languages, people who invent programming languages like to be very succinct, to the point, so we tend to use fairly short phrases to describe things, not necessarily full words. So while you might say string, technically in Python what we're really talking about, these sequences of text, are technically strs. This is an actual type of data in a program. But we'll soon see that there's other types of data in programs as well. In fact, let's see if we can't improve this in one other way. I like the progress we've made by keeping everything on the same line. Hello, comma, David. All on the same line. What more, though, could we do in terms of solving this problem? Well, it turns out that we didn't have to give up entirely with using print twice. Let me rewind a little bit and go back to that earlier version where I wasn't really sure how to solve this problem. So I was using print once to print out just the hello and the space and the comma. And then I used print again.
Will help MIT OpenCourseWare continue to offer high-quality educational resources for free. To make a donation or view additional materials from hundreds of MIT courses, visit MIT OpenCourseWare at ocw.mit.edu.
Welcome to 5.11.1. And today what we're going to do is introduce you to the course and the people teaching the course. And we're also going to let you know that you are going to be part of the great web exercise that is OCW, OpenCourseWare. So this course is being videotaped this year, and this is the announcement that I have to make. So the videotape is in the back, and if you want to come up front and participate in the class, you'll know that you'll be videotaped. If you want to hide your face or whatever, you can do that, but please pay attention to the lectures anyway. So this course will be available on the OCW site in the future. I'm not sure exactly what that date is going to be. So today we're going to introduce the chemistry topics, which we will cover in 5.11.1, and give you general information, practical information about the course, number of points you need, when the exams are, that kind of thing, policies, and introduce you to the teaching staff. I am, again, Professor Kathy Drennan, and I'm one of the lecturers in this course. So because this is MIT, we're going to start with a quiz. Okay, not a quiz for points or anything, don't freak out. But I do want you to tell me who these people are. So what about this person? That's me. This is my college yearbook photo. Okay, what about this person over here? It's not me again. Not Elizabeth Taylor. It is Lisa Kudrow, known as Phoebe on Friends. So we both went to college at the same time. We went to the same college. Does anybody know what college that was? Vassar College, very good. And we graduated the same year. Now, no one has to say what year that was, even if you know. But we did graduate the same year. All right. So, given what you know about us, what do you think Lisa went to college to study? Computers? No. Theater? Surprisingly, no. Nuclear engineering at Vassar, no, for a variety of reasons. Any other guesses? English, no. Biology. I heard it. Biology. What do you think I went to college to study? Theater, correct. And, or, I hadn't made up my mind exactly, biopsychology or drama. So biopsychology was what they called sort of brain and cognitive sciences in those days. So those were the two things I was thinking about. What do you think Lisa ended up majoring in college? Theater? No. Not biopsychology. Biology, yes. What do you think I majored in college? This should be a bit easier. Chemistry, correct. And of course, our professions, actress and chemistry professor. So one may ask, what happened here? My understanding about Lisa Kudrow is that she came from a Hollywood family. She went to college and said, here's my opportunity to study the thing that I find most interesting, and that was biology. And then she went back and participated in the family business, which was, of course, the acting profession. For me, what happened? Well, I have to say, I did not like chemistry in high school. So I did not think about going to college to study chemistry. So why did I not like chemistry in high school? I think it was because of images such as this one. I spent a lot of time talking about the transition between alchemy and modern chemistry. I wasn't very interested in that kind of thing. And there was nothing in these photographs that really appealed to me personally. I mean, Avogadro, I'm fond of his number, and he is, in fact, an interesting, if not frightening-looking man. This just didn't connect with me. But then I got to college, and they said, well, if you're thinking about anything biopsychology, biology, you have to take chemistry. And I said to my advisor, no. I have taken chemistry in high school, and I can assure you that chemistry has no relevance whatsoever to the life sciences. And they said, well, sorry you feel that way, it's incorrect, and you have to take it anyway. So I, like some of you in this room, took freshman chemistry because it was actually a lot of fun, and that the chemistry I got in college was pretty much nothing like the chemistry I had seen in high school. So let me introduce you to some of the topics we're going to be covering in chemistry this semester. So there's more detail on your syllabus, a detail of what we'll cover every day. But these are the kind of basic things that we're covering. And you don't need to write this down. You'll become familiar with it as the semester goes on. We start out with some really basic principles. So up here, atomic theory, periodic table bonding, structures of molecules. And there will be a little bit of history in there. But this is mostly modern chemistry and represents the basic properties of matter. And it's the basic properties of all matter, including living matter, which was what really interested me, that connection between chemistry and biology. So then we go on to thermodynamics and chemical equilibrium. And this is really about reactions, chemical reactions, whether a reaction will go, will it be spontaneous? If there's an equilibrium, what direction will the reaction be shifted in? And then, of course, not just whether the reaction will occur, but how fast it occurs is really important. So that's kinetics, how fast a reaction will go. And from the perspective of someone who's a biochemist, I'm interested in kinetics and enzyme kinetics and in thinking about molecules that catalyze reactions in the body. And then there's acid-base equilibrium and also oxidation-reduction reactions. And what is true is that most reactions that occur are either catalyzed by some kind of acid-base catalysis or involve some kind of oxidation-reduction reaction. And so this sort of represents a lot of the basic way reactions go. Now, whether that's a reaction in your body or a reaction in a test tube, it doesn't matter. A lot of the same principles are involved. And then we also cover transition metals, which is something that you often don't see in high school. And transition metals, those metals in the middle of your periodic table, have some really unique properties, which are exploited again in reactions that occur in your body and also are utilized in industry, for example. So we'll talk about some of those unique properties. And if we put all of that together, we get the real fundamentals that you need to go on and study any kind of curriculum that involves chemistry. So these are all the fundamentals that are involved in chemistry that relate to physical chemistry, organic chemistry, inorganic chemistry, biological chemistry, and are a solid foundation for studying any kind of life science. So I congratulate you on being here in this class. This is really good, solid foundation for whatever you go on to do here at MIT. So normally at this point, we do actually start the class with a little bit of history from alchemy to modern chemistry. But I decided to skip that this year. If you are interested in that, it's never required on any test. It never has been. But if you're interested in that, there is an OCW lecture which you can listen to. That's an excellent lecture by Professor Sylvia Sayre on that. But today, instead, I thought I would give you some examples of modern chemistry. Why people now need to know chemistry, what they're doing with chemistry, what is chemistry research here at MIT, and how does it utilize these basic principles which we'll be talking about in the course. So start with my colleague, Professor Joanne Stubbe. She studies molecules. In particular, she studies biological molecules. And one of the things she's very interested in is how this anti-cancer drug, gemcitabine, works in the body. So it inhibits an enzyme, and she's interested in knowing how that really works. So enzymes are made up of amino acids. You have long chains of amino acids that form together into a protein molecule. Protein molecules in your body often act as enzymes, catalyzing reactions. So she is interested in how this molecule, gemcitabine, inhibits an enzyme. So to do those studies, she needs to know a lot of the stuff on this list. Of course, she needs to know the basic principles, but she's also talking about an enzyme, so she needs to know about enzyme catalysis. She needs to know this enzyme works by both acid-base chemistry and oxidation reduction. It has two irons that are involved in doing the chemistry, so it includes transition metals. She thinks about how things bind, how the natural reactants bind, how the inhibitor binds, and so she needs to know what happens to the chemical equilibrium. She needs to know about the thermodynamics of those binding events, and of course, everything, all the basic principles are required here. So to do this biochemistry research, she needs to know all of these things, and she has really made tremendous progress in understanding how gemcitabine works, and it is not so toxic, so it's a really good thing to have in chemotherapy. So in addition to studying molecules, chemists often want to make molecules, such as Tim Jameson, who's an organic chemist. So you will hear probably, hopefully, in this presidential debate about the environment and about why saving the environment is important. And one of the things you often hear about in this discussion is about our oceans and about rainforests. And part of the reason why people want to protect those areas is because you find a lot of natural products in those regions. So a natural product is something that is made by nature, and often natural products, whether it comes from a plant or a marine organism, have some really good, useful properties. And so one particular compound has anti-tumor properties, so again, along this line of cancer research. So Tim Jameson's lab figured out how to make this thing. And often that's really important because you can't get enough of the organism that naturally makes it to be able to grind that organism up and have enough that you can actually use as a medicine. So you have to make more of it because nature doesn't make enough. So it's very important to figure out how to do that. So in doing that, Tim Jameson's lab needs a lot of these things. So he needs a lot of knowledge of bonding. He wants to form bonds in making this. He needs to know about the structures of the molecules because if the structure is wrong, it's not going to work. And often if you want to make a lot of it, you have to think about the thermodynamics of the system, how fast the reactions will go, and kinetics, and then whether they'll go, the thermodynamics. And sometimes then you need to adjust the reactions, maybe use a transition metal to make it go better. So these are all the things that Tim Jameson needs to know to do organic chemistry. So you'll be learning in this class a great preparation for 512, which is organic chemistry. In addition to studying molecules and making molecules, some chemists want to detect molecules. And a chemist who likes to detect molecules is Tim Swager. So Tim Swager's lab has designed sensors that detect vapors. And so they will detect TNT, for example. And so he has put this chemistry to use in this robotic arm, and they call it Fido because often dogs are the creatures that have to go out and detect these things. And it's not a great job if you're a dog to be sent out to see whether there was an explosive and discover, yes, there was, a little bit too late. So this is a much nicer way to detect chemicals with this robotic arm. And here's a picture of it in use in Iraq. So in doing this, if you go down to kind of the basic principles that Tim needed to know about, oxidation reduction was really key in developing this technology. So we'll talk about that. So my final example is from Alan Davison's lab. And Alan is an inorganic chemist. He loved those transition metals and their unique properties. And he designed this compound. It's called Cardiolite, and it's used in heart imaging. So many people have relatives they know of that have had to have their heart imaged. Heart disease is a major problem in the United States, and there's a good chance that they had Cardiolite given to them to help in that imaging process. So this, again, takes advantage of those great, unique properties of transition metals, which we'll talk about in this course. So again, all together, this is the basis for modern chemistry. And the examples I just gave you were some of the things that modern chemists are working on, some of the issues that our country faces and our world faces, and how chemistry is involved in that. So not only will you have the fundamental knowledge to go on and take more courses in chemistry, you will also have the fundamental knowledge to go on and do undergraduate research here. And here are some of the 511-1 undergraduate researchers that have come through my lab in particular from this class. So it's a really nice, solid foundation. So I want to encourage you to set some of your likes and dislikes from high school aside when you come to MIT, because at MIT you often see disciplines taught and emphasized very different fashion than what you've seen before. And you may discover that the thing you came here to study is not the thing that you really want to study after all. One other thing that I'll say to you is that I said these words at one point. It's true. I said, when I was in high school, I said, I hate chemistry. And now I do chemistry every day and will for the rest of my life. I love chemistry now. Be very careful what you say. Have any of you made that statement about hating a subject? Tell me later what it is you're going to be doing for the rest of your life. So at MIT, things are very different. And keep an open mind. Explore new areas. Take advantage of being at this amazing place for science and technology. And you may surprise yourself in what you really enjoy learning about. So that's a little bit about the chemistry that we're going to cover in this class. And now I'm going to talk a little bit about some of the policies and procedures. But first I need to introduce my co-instructor for this class. And let me just put up her picture. You'll see her in a minute. So Dr. Beth Fogel-Taylor. So all chemistry courses are team taught. So you have a different lecturer for the first half than the second half. And Dr. Taylor will be doing most of the first half lectures, and I'll be doing most of the second half lectures. So Dr. Taylor will take you from atomic theory through thermodynamics, and I'll start up with chemical equilibrium, talk to you about kinetics, acid-base, oxidation reduction, and transition metals. So you will have both of us as lecturers in this class. Now, in the past, sometimes students have found this whole thing a little frustrating, that they just get used to one lecture style, and then all of a sudden there's another lecture style. And that can be true. I mean, sometimes the styles of the two professors, couldn't be more different. Think McCain-Palin. Odd couples. Sometimes they're more similar. And when I first, about a year and a half ago, got to know Dr. Taylor, we sort of realized that we had very similar styles. And we got very excited about the idea that we could teach together so that there would be much more continuity throughout the semester. And so Dr. Taylor had been teaching the first half of the material in the spring, And I had been teaching the second half of the material in the fall. And we thought, wouldn't it be great if we got together and taught in the fall? So this was actually, for a variety of reasons, a very complicated thing to request and do. And so we started a campaign and campaigned for a year and a half that we should be allowed to do this course together. And finally, just a few weeks ago in August, we really didn't know up until almost when this course started that permission was granted. So I have to say I am very excited now to introduce you to Dr. Taylor, who I will be teaching with this semester, limited engagement, who will tell you about some of the course policies.
Great. Thanks. Okay, so before we get to some of these course policies, I think I'll tell you a little bit about my path to chemistry as well. Professor Drennan explained that not everyone that ends up as a chemist started off that way on their first class, freshman year, for example, in chemistry. And in fact, if you talk to a lot of chemists, if you talk to some of the graduate students, maybe your TAs, you'll find that that phrase, "I hate chemistry," has maybe been uttered by more than one of us at some point in our lives before we realized, and once it happens, you don't go back, that actually you love chemistry, and it's hard to even remember a point where you didn't see all of these connections that it provided for you. But to give a little background of where I was sitting, where maybe you are today on the first day of chemistry, when I left high school, I had no interest in chemistry whatsoever. And I have only one strong memory from high school chemistry, and that memory is shown right here, and that is the common ions. Did you guys have to learn the common ions? Does anyone have that in their brain somewhere for ready use? I don't, in fact, so it's actually okay if you don't know all your common ions, if you missed that part. This is the strongest memory I have. And I remember at A that I didn't learn them, and that was really bad because it kept coming up. But the other thing I remember is that I had no idea why they were important. I didn't really understand what any of these molecules were. I certainly didn't understand how they even connected really to chemical reactions, much less other disciplines that I was interested in. I couldn't have told you, for example, if we look at a phosphate group, that that's going to be incredibly important in DNA, that it's also an incredibly important group when you're dealing with proteins and whether you're turning the function of a protein on or off. So really, I just had no context for the chemistry. So when I started in college, that wasn't even an option for me, and I was interested in a lot of things, chemistry not being one of them, but one that I was very interested in was biology. And the reason was, we did a lot of cool labs in high school. I loved doing the dissections. It was very interesting to me to think about how different organs worked, how the heart could be a pump, how the lungs worked. And then when we got to more of a cellular level, it was even more interesting to see that we could actually understand how our body worked as low of a level as thinking about cells. And so that was a clear major for me to pick. I actually also was considering English and ended up being a minor in English, but I think what most of you actually, having come to MIT, have probably realized is sometimes it's nice to major in a science because you can't just pick up a reaction and do it in your kitchen on the weekend, whereas you can sometimes join a book group and do that. So it's kind of nice to major in the thing that you're going to get to have the opportunity to do for the rest of your life. So I actually also started pre-med. Is anyone else pre-med here? Okay, so a pretty good showing. So maybe you can relate to some of the reasons I wanted to be pre-med. Part of it was the interest in the science and the biology. Also, I wanted to help people. It seemed like a really clear way that I could have a career that was challenging and involved in science, but also helping others. So it seemed like a good start for me, pre-med bio. And I signed up for my bio class. I found out, as Professor Drennan did, that I had to take chemistry as well. I wasn't as upset. I was sort of a neutral chemistry person at this point, but I thought it was pretty smart to get it over with on the first semester, so that's what I did. And my plan was going along fine until something happened, and what happened was that chemistry was just way more interesting than I'd anticipated. So my perfect pre-med bio plan was getting a little shaken right from the start. And the reason that it was getting shaken was because I would learn this new principle in chemistry, and because I was taking bio at the same time, I could see the connections. And at one point I realized, oh my gosh, chemistry is just biology. It's just looking at it one level deeper. So actually, all of my interest in biology was quickly transferred to saying, wow, now I can think about things on the molecular level. And one of the molecules that caught my attention first, and I can't remember if this was freshman or sophomore year in high school, was the first time I actually took meaning in looking at a chemical structure, and that was with the structure of penicillin here. And I know that all of you are familiar with penicillin, whether or not you know the structure or not. But the most important part of this structure is the four-membered ring here, the beta-lactam. And this was the first time I thought I could actually understand how a molecule worked because I knew something about chemistry. So for example, with penicillin, what it does is it inhibits an enzyme that builds the cell wall in bacteria, the bacterial cell wall. And if I thought about what I'd learned in chemistry, some of you know this from high school, some of you will be very familiar with this soon, is that this carbon here, for example, is bonded to three things. Does anyone know what angle those would like to be at? 120. They want to get as far away from each other as possible. The ideal angle is 120. But what we have here is a four-membered ring. So what angle does that have to be, that bond? 90 degrees. So we have a problem here if we're thinking about keeping things at the lowest energy. So there's a lot of ring strain in this system. And I was incredibly excited that I could look at that and realize it and say, wow, that's why it's so reactive. That's why it's such a good medication. Because when it comes into contact with these bacterial cell wall building enzymes, the enzyme can actually react with this four-membered ring and open up the ring and relieve that ring strain. So now the angles can open up all the way to 120 if it wants to, and there's no way it's going to form that ring again, right? Because it's not going to go back to those 90-degree angles if it can help it. So now the enzyme is locked up with the penicillin molecule, no more bacterial cell wall being built, and the penicillin has effectively killed the bacteria. So that for me was kind of the first connection that went, whoa, wait a second, I want to be thinking about these molecules all the way down to the level of individual atoms. So at this point, kept the pre-med, just switched the major to chemistry. The next problem came up when I went and took organic chemistry. So if you're dead set on staying with bio, maybe, I guess you have to take organic. So this might happen to you, just to warn you. We started looking at all sorts of other kinds of molecules that became very interesting to me. I especially love thinking about vitamins and drugs because I do have that interest in medicine and human health. These are actually all examples that we'll talk about in freshman chemistry at some point as an example of a connection between a chemical principle we learn and what we can know about how it functions. But what happened here was I thought, oh my gosh, now I could actually, using my chemical knowledge, think about synthesizing these molecules or maybe coming up with new ways to synthesize them better or synthesize different molecules. And the real clincher was when I started doing some undergraduate research. Any potential UROPs out there? Anyone planning to do research at some point? Excellent. Okay. So just to be warned, you might fall in love with the subject you do your UROP in. This is one of our summer students from this past summer who is also pre-med. She's continuing to be pre-med, which is fantastic. That didn't happen to me. Once I got into the lab, I didn't want to leave. So I thought, you know what, I think I'll change the medical school plans, and now I'm going to go all the way. Chemistry major, chemistry grad school. And the reason I was able to do that and keep with what my original intentions were was to have a career that was fulfilling in terms of helping people and being engaged in science, is all of a sudden I realized, as chemists, we can think about better ways to build molecules that are important for making medications. Another thing we can do is we can use our chemistry to understand biological systems, so we can help elucidate pathways maybe that are implicated in disease. So the combination of these two things had made my decision, and I ended up coming here for graduate school, actually, and working in Professor Imperiali's lab doing bioorganic chemistry, which means that I synthesized molecules, which I loved, and used them to study biological systems. So really, I'm pretty happy with what I've gotten to do. And I just want to say we're not trying to convert all of you pre-med people by any means. My roommate for many years was going to medical school as I was going to graduate school. And we found we had so many interesting conversations about chemistry, her from the context of practicing and using medications and talking about how they worked on a molecular level, and me talking about my research.
The following content is provided under a Creative Commons license. Your support will help MIT OpenCourseWare continue to offer high-quality educational resources for free. To make a donation or view additional materials from hundreds of MIT courses, visit MIT OpenCourseWare at ocw.mit.edu.
So our first question here is about limiting reactants. So that's something you will encounter in your review reading for the sections that kind of review what we hope you have picked up from high school or will pick up quickly by doing some review. So how about we have everyone take 10 more seconds on the clicker question, get your final answer in here. All right, so let's see what we have. All right, so it looks like we weren't showing the percentages here, but it looks like hopefully most of you were able to get the correct answer of H2 being the limiting reactant. Looks like we're still figuring out. This room was just renovated. We're still working out exactly how the electronics work. So normally we'll see a percentage of how many of you got it, but I'm going to say it was probably about 95% got the answer right. So good job there. If you didn't get the answer right, we'll send these questions to your TA. So anytime you get a clicker question wrong and you're confused, bring it up in the next recitation section and you'll be able to discuss it there. So starting in, we can switch over to the notes now. When we left off on Wednesday, what we had really been doing is trying to give you an overview of all of the different topics that we're going to be going over this semester, and also to make a couple of those connections between the principles we're learning and some of the exciting research that's going on at MIT in the chemistry department, and also to give you the idea that we are going to be trying to make these connections between the chemistry and things like human health or medicine. So now we get to actually take a step back and start at the beginning, because before we can talk about some of the more complex issues which involve interactions between molecules reacting, or even when we're talking about individual molecules, the bonds that form between individual atoms, before any of that, we actually need to establish a way that we're going to describe and think about how an individual atom behaves. And the way that we'll do this is starting with talking about the discovery of the electron and the nucleus here. Once we go through that, we will be able to talk about describing an atom using classical physics. So once we have an atom and a nucleus, what we'll try to do is apply the classical mechanics to explain how that behaves. What we'll find is that this fails, and once this fails, we're going to need another option. Luckily for us, we have quantum mechanics, which we'll be talking about for the next few lectures, and we'll dive into that. We might get a chance to introduce it today, but certainly in next class, we'll be introducing this new kind of mechanics that's going to allow us to describe the behavior of atoms. So I want to point out that it makes a lot of sense for us to start with the discovery of the electron and the nucleus, because it really highlights one of the big issues that comes up in all chemistry research that you do. And that is, how do we actually study, or in this case, how do we discover atoms or subparticles that we actually can't see at all? And there are lots of solutions that chemists come up with. There's always new techniques that allow us to do this, and these are just some of the first, and we'll go through them in a little bit of detail here. So this all starts in terms of putting it in its historical context at the turn of the century. We said we'd start right in on the 20th century of where chemistry was. And where we were at the start of the 20th century in the late 1890s is that we were at a place where there was great confidence in our understanding of the universe and our understanding of how all matter worked. So people in the chemistry community and in the physics community had this general feeling that the theoretical structure of the entire universe was pretty well understood. And they had this feeling because there had just been this huge boon of discovery, of scientific advances that included Newtonian mechanics, and included Dalton's atomic theory of matter, also thermodynamics and classical electromagnetism. So you can understand they really felt quite confident at this time that we could explain everything that was going on. And in fact, a really telling quote from the time was said by a professor at the University of Chicago. And what he said is, "Our future discoveries must be looked for in the 6th decimal place." So basically what he's saying here is we pretty much understand what's going on. There's nothing new to really discover. All we need to do is measure things more precisely. So that's not exactly the case. And we're going to start in at the point where right around this time of great confidence, of feeling all has been conquered, there are some observations and discoveries that are made that completely break down these theories. For example, in terms of the atomic theory of matter, at the time, at the turn of the century, the understanding was that atoms were the most basic constituent of matter, meaning you couldn't break atoms up into anything smaller. That was it. You're done. And with using Newtonian mechanics, it was assumed, since this type of mechanics worked so well to describe everything we could see, it could even describe the universe and planets, that of course we could use Newtonian mechanics to describe how an electron, actually we didn't even know about an electron here, but how atoms behaved. And it turns out this is not the case. And the first step in discovering this is not the case was accomplished by J.J. Thomson. And J.J. Thomson is credited for discovering the electron. He was a physicist in England, and what his laboratory was studying is something called cathode rays. And cathode rays are simply rays that are emitted when you have a high voltage difference between two electrodes. So if you look at this setup, what he did when he was studying these rays is he had an evacuated tube, which is schematically shown here, where it's evacuated of all its air and filled instead just with hydrogen gas. And he had this high voltage difference between an anode and a cathode, and he actually put a little hole in the anode here, so these cathode rays that were produced could shoot out of the cathode and actually could be detected as this luminescent spot on a detector screen. So lots of people were studying cathode rays at the time. One reason is they actually gave off this bright glow. If you put them in an evacuated glass tube, you got these crazy patterns and glowing colors. So for that reason, it was a very hot issue in terms of research. But also, no one really knew what these were. And Thomson was seeking to figure out some more properties of them. And he had the theory that maybe they were actually charged particles of some sort. And others had proposed this in the past, but they didn't really have an experimental setup to test it. And that's what Thomson did. And what he did was he put two detection plates on either side of these cathode rays. And when he put a voltage difference between those two plates, he wanted to see if he could actually bend the rays and test if they're actually charged or not. So when the voltage difference between the plates is 0, or when we just don't have the plates there at all, the cathode rays are not bent. They just go right in a straight line, and they can be detected on this screen. When he actually cranked up the voltage between these two plates, what he saw was really amazing to him, which is that he actually was able to bend these rays. This had never been observed before in any capacity, and he was able to detect on his screen that there was this deflection, and he could even measure the degree of deflection that he had. So we know now that we have charged particles. Are these negatively or positively charged based on this evidence? Yeah, that's right. So what we have here, cathode rays, we now know, are negatively charged particles. And in fact, he named these negatively charged particles. Does anyone know what he named them? No, not electrons. Very good guess. He named them corpuscles. Has anyone heard of corpuscles? A little bit. Yeah, so it was later named that these particles were in fact electrons, and that's what they are. J.J. Thomson continued to call them corpuscles for many, many, many years after everyone else called them electrons, but I'm sure no one minded because he did in fact discover them. And he was actually able to find out more than just that these were charged. From classical electromagnetism, he could actually relate the degree of deflection that he saw to the charge and the mass of the particles. So using that, he could say that delta x, and we'll put sub-negative because we know now that these are negative particles, is proportional to the charge on that particle over m, which is the mass. So we have E being equal to the charge of the negative particles, and m, of course, is equal to the mass of those particles. So Thomson didn't stop here. He actually continued experimenting with different voltages. And what he found was if he really, really ramped the voltage up between those two plates, he could actually detect something else. And what he could detect here is that there's this little spot of luminescence that he could see on the screen that was barely deflected at all. Certainly in comparison to how strongly this first particle was deflected, the second particle was deflected almost not at all. But what he could tell from the fact that there was a second particle at all and the fact that it was in this direction is that in addition to his negative particle, he also, of course, had a positive particle that was within this stream of rays that were coming out. So, of course, he can use the same relationship for the positive particle. So delta x now of the positive is proportional to the charge on the positive particle all over the mass of the positive particle. So this is interesting for several reasons. What did he manage to pull out information-wise from using these two relationships? And actually, to do this, he made a few more observations. The first, which I just stated, is that the deflection of that negative particle was just far and away more extreme, much, much larger than that of the positive particle. The other assumption that he made here is that the charge on the two particles was equal. So how could he know that the charge on the two particles was equal? And actually, he couldn't exactly know it. It was a very good assumption that he made, and he could make the assumption because he, in fact, did know that what he started with was this hydrogen gas. So he was starting with hydrogen. If some negative particle was popping out from the hydrogen, then what he must be left with is H+. And since hydrogen itself is neutral, the H+ and the electron had to add up to be a neutral charge. So that means the charges of the two pieces, the positive and the negative particle, must be equal in terms of absolute charge. So using this relationship, he can then actually figure out, by knowing, which he knows how much each of them were deflected, he could now try to think about whether or not he could make some relationship between the masses, between the mass of the positive and the negative particle. So this relationship he was looking at was starting with the deflection and the absolute distance that the particles were deflected. So what he could set that equal to is he knows what x is proportional to in terms of the negative particle. So that's just the absolute value of the charge over the mass of the negative particle. He could divide all of that by the absolute value of the charge of the positive particle all over the mass of the positive particle. And as we said, he made the assumption that those two charges were equal. So we can go ahead and cross those right out. So what that told him was if he knew the relationship between how far they were each displaced, he could also know something about the relationship of the two masses. So essentially, there was an inversely proportional relationship between how far the particles were displaced and what the mass of the two particles turned out to be. So because he, of course, observed that the negative particle traveled, it was deflected much, much further by those plates, what he could also assume and make the conclusion of is that the mass of that negative particle is actually larger or smaller? Much, much smaller, exactly, than the mass of the positive particle. So essentially what he found here is the relationship between the mass of an electron and the mass of the rest of the atom, the rest of the hydrogen atom there, which is an ion in this case. And in fact, it's so much smaller, it's close to 2,000 times smaller, that we can make the assumption that essentially the electrons take up no mass. I mean, they take up a teeny bit, but essentially when we're thinking about the setup of the atom, we don't have to account for them as using up a lot of the mass we're discussing. So Thomson came up with a model for the atom due to this, and this is called the plum pudding model of the atom. And he was, as we said, English, so plum pudding is kind of a British food. Has anyone here ever had plum pudding? A couple people? Okay, I've never even seen it, so that's good. You must be better traveled than I. So the idea that he had here was he treated the whole of the atom as sort of this positive plum, or this positive pudding. So the majority of the atom was just kind of this goopy positive stuff that you could think about. And within the pudding, he had all these negative charges, which were the electrons, and they were the raisins or the plums that were in the pudding. So this was a revolutionary model of an atom when we thought of the fact that before this experiment, the understanding was an atom could not be divisible into smaller parts. And now here we are with subatomic particles with electrons and this wonderful plum pudding model. So for those of you that haven't actually had plum pudding, which myself was included, I threw a picture up here. This was my first glance at plum pudding. And I guess you can see that this must be that positive part. Most of the plums are within that, and you can see all these little raisins or plums in here. That would be that negative charge. So that already was a big advancement from where the understanding was at the time. We'd already moved way forward and completely revolutionizing the understanding of an atom in that there's something in an atom. It's not the smallest thing there is. However, as you know, we didn't stop at the plum pudding model, which is good because it's a little goofy, so it's nice to move on from that. And move on we did about 10 to 15 years later. Another physicist, Ernest Rutherford, actually put this plum pudding model to test. And he did it through studies that he'd been doing on radiation that was emitting something called alpha particles. So Rutherford, some of you may recognize that name, is a very famous physicist who made a lot of contributions in terms of radioactivity. When he was studying these alpha particles, he was actually the first person to identify the difference between different types of particles that radioactive materials emit. And he got this particular material that he was studying, radium bromide, from his good friend Marie Curie, who obviously also was a leader, really the leader in figuring out much of how radioactive materials work. She has 2 Nobel Prizes for her work in radioactive materials. And something that maybe many of you think, which I know I always think when I hear about radioactivity studies in the early 1900s, is, oh my gosh, this sounds really dangerous, right? They're using radium bromide, and this is a pretty dangerous radioactive material. So for those of you that don't know, radium is extremely radioactive, even in the range of radioactivity. And one of the major problems with it is that if it does get in your body, the radium is treated as calcium in your body. So you can imagine what happens is it gets deposited into your bones, which is not the ideal situation after a long day in the lab. So, this is really a pretty dangerous situation. That's always interesting to point out. He got this from Marie Curie. You can imagine they used the Postal Service. I'm not sure how else they would have transferred it to each other. So it really brings up some issues. The first thing I did when I heard this is actually look up to see how, in fact, Ernest Rutherford did die in 1937. And you'll be happy to know it actually wasn't from radiation poisoning or from bone cancer. So that's really good that worked out okay for him. And that he did get to sort of safely at least end his life before the radiation ended it. But it's really interesting, the studies that he did do with radium bromide, and he was studying the alpha particles. And what was known about alpha particles at the time is that they were these charged particles and that they were very heavy. Does anyone know more than what Rutherford knew at the time what alpha particles actually are? Yeah, good. So they're actually helium atoms, helium ions. And this wasn't really important for the studies. It didn't matter that he didn't know what they are, but it's nice to kind of note now that we do know what they were using. And he was doing quite a few studies with them. One experiment that he was doing is detecting the number of particles that were being emitted by this radium bromide as a rate. So he would measure the number of particles per minute that the radium bromide was emitting. And what he used was a detector here so he could detect how many particles were hitting this detector. He'd actually developed this detector with a postdoc by the name of Hans Geiger. Does that name ring a bell? The Geiger counter. So this, in fact, is my very schematic representation of a Geiger counter. For those of you who don't know what that is, it's simply an instrument that counts